All right, this is lesson 2.2 of our calculus class. Unit 2 is called derivatives. Lesson 2 is called instantaneous rate of change. And so this is a continuation of the idea in our first lesson, average rate of change. And what we're doing is we're building a conceptual understanding for what we are going to learn about in the future, which are derivatives. So in this lesson, we're going to define instantaneous rate of change at a point. And we're going to look at how does a tangent line relate to instantaneous rate of change. So instantaneous rate of change. Graphically, what that means is at a specific point. So some point A, we have how steep is this line at specifically just this point. Over the whole line, the steepness of the line is constantly changing because it's curved. But specifically at this point, how steep is that? Graphically, I can draw a line that's straight that will touch this curve at exactly that point x equals a only. Not cut through it like a secant line, but just touch it. It's just a nice little touch on the surface. This would be called a tangent line. A tangent line is a line that just touches the graph of a function at just one point. If we continue this line away from x equals a, the graph may cut through it at another point or touch it somewhere else. That's kind of irrelevant. But it's tangent exactly at this point A. All right, so instantaneous rate of change. If we look at our definition of average rate of change, we have some purple function defined right here. And let's get this a little closer, zoomed in. And I want to find, okay, so what's the tangent, or the, words. So if a is equal to 1 and b is equal to 2.4, and I find this f of b minus f of a over b minus a, what this is the definition for a secant line, or the slope of a secant line, or the average rate of change. Now, when I want to find is at, well, basically at one point, what's the instantaneous rate of change? So that would mean that if a point I want to find is 0.1, our definition for average rate of change doesn't work for instantaneous rate of change, because if you have the interval be from 1 to 1, well then f of b is f of 1, and f of a is also f of 1, and b is also 1, and a is also 1. So we'd have f of 1 minus f of 1 over 1 minus 1, which would be 0 over 0, which if we learned anything from last unit, would be like indeterminate form. 0 over 0 doesn't work, it's not defined, can't do it, however you want to say that. So we kind of have to extend beyond our average rate of change definition in order to find instantaneous rate of change. So, and that's exactly what I just said. So what we're going to do is we're going to look at our average rate of change function, but we're going to apply a limit function to it. So if our interval is from a to a plus h, I want to find the limit as h approaches 0. So what that means is from a to a plus h, as this limit, we can't say it equals 0 because we get indeterminate form, but as h approaches 0, so as this interval gets infinitely close to nothing, and as a plus h gets infinitely close to a, what would this difference quotient look like with that limit function applied? And so this is going to be our definition for instantaneous rate of change. And yes, on the bottom we have a minus a, so we can cancel that out and just write our definition for instantaneous rate of change to be the limit as h approaches 0 of f of a plus h minus f of a over h. So this is the definition we're going to work with for instantaneous rate of change. All right, so a tangent line. Similar to a secant line, a tangent line is the line that touches the graph at just that one point. The slope of the tangent line is the instantaneous rate of change of the function at that point. So if I want to find the instantaneous rate of change, or the slope of the tangent line for the given x values, I can do so with our limit function. So if for a, at x equals -6, our a value is -6. So f of -6 plus h minus f of -6 over h, and the limit as h approaches 0. This is how we'd set that up right there. Here's where our tangent line would be at x equals -6. Boom, boom. And we could evaluate that. So let's see here. Well, yeah, we're going to leave it at this for now. If we did -2, we'd have the same setup, but we'd have -2 in place of -6. And if we wanted to find the tangent line slope at x equals 1, it'd be the same setup, but we'd have 1 in place of the -6 on both spots. All right, so here's our function. Instead of a graph, it's just a function. F of x is equal to x squared minus 1. What is the slope of the tangent line at x equals -2? Well, we're going to plug in -2 for our our a value. So we have the limit as h approaches 0 of f of -2 plus h minus f of -2 all over h. And now we do know that this is a x squared minus 1 is our function. So I can replace x squared minus, I can replace f of -2h and f of -2 with this function right here. Instead of x, we'd have -2 plus h. So -2 plus h squared minus 1, and then minus -2 squared minus 1. And we can simplify this further, but for now, this is as far as we're going to go. We don't really need to waste our time doing some calculations here. Not just yet. So here's our line that we've graphed. We can see our tangent line. Let's see here. So our x value was -1, sorry, -2. So if we look at f of -2, we get 3. Let's find that in the graph. Whoa. Here it is. So at this point, we can see we'd have a tangent line that is, did I get that? Yeah, blue one. Our tangent line is right there. It's going to touch the graph exactly at just this point right here, -2, 3. If we zoom in, we will see that it's not actually going to cut through the graph. It's just going to touch it, just that point. And this is not super clear as I would like it to be, but it gives you the idea. So the slope of this line is -4. That would be the instantaneous rate of change, but we'll unpack that a little more. Okay, so here's another function. It's basically the same setup as before. If we're looking for the tangent line at x equals 0, 0 is our a value, and so the limit as h approaches 0, we could write with this setup right here. And you know, the fact that we're not actually finishing the calculations here might seem sus to you, but we're really just trying to save some time at this point because we'll do a lot more calculations with this in future lessons. And please forgive the Among Us reference. All right, takeaways for this lesson is we can calculate instantaneous rate of change at a point. A tangent line is a line that touches the graph of a function at just that single point, and the slope of the tangent line is equal to the instantaneous rate of change at that point. We have a formula for calculating instantaneous rate of change, and it is the limit as h approaches 0 of f of a plus h minus f of a over a plus h minus a, which is really the same thing, can be simplified as a denominator of h. And we could do that for any point x equals a.